Yeah, hello everyone. My name is Veronika, and I'm leading the efforts of developing the CatBoost library. Today I'm going to give you a tutorial on gradient boosting with CatBoost. That is the instruction what you should download before the tutorial. I really recommend you to download this and to try everything with your hands. It will be I will help you with everything, so it will be pretty easy I hope it will be easy to follow. So here are the slides, or here are the files. That is a link to the slides. That has also the first slide with all the materials to download. What will happen now? I'm going to give you like 10 to 15 minutes overview of what is the library that I'm going to show you. And then we will go through all the practice with our hands. We will use Python for that and Jupyter Notebook. So it would be really nice if you would have Python and Jupyter Notebook on your laptop, that you probably do if you are on this conference. So I will show the slide with the download materials one more time after I'm done explaining what is CatBoost. By the way, who of you has ever used CatBoost? So 3 people. Okay, good. And who of you has used XGBoost? Also not everyone. So anyway, if you already have used XGBoost, then it will be super useful for you. If you have not used CatBoost or XGBoost, then you will just start with gradient boosting and you will love it, so it will be useful for you too. Let's start. CatBoost is a gradient boosting library. It's an open source. It's the newest gradient boosting library of the several open source ones. There is XGBoost, LightGBM, and CatBoost. And we are in open source for about 2 years. Now, yeah, as I told you, I will tell you a little bit about CatBoost first. So I will first give you some introduction about what is gradient boosting, and then I will show you some benchmarks, how CatBoost compares to other gradient boosting libraries, so that you know how to choose. And then we will have the tutorial. And then after we finish the tutorial, I'll tell you a little bit about what we are working now on and what you will see in the next releases in the close future. Okay, so what is gradient boosting? Gradient boosting is a machine learning algorithm that has several advantages. First of all, it works really well with heterogeneous data. So there is homogeneous data, like images, sound, or text, or video. And for this type of data, you need to use neural networks. And there is heterogeneous data, that is table data. For example, if you are predicting credit scoring, then one sample will be a person, and it will be described with a set of features like salary, age, gender, credit history. For these types of data, gradient boosting usually gives the best solution. And because of that reason, gradient boosting is heavily used in production of many, many companies. And it is also used for machine learning competitions, and you can see on Kaggle for this table data, most of the competitions are won by gradient boosting solutions. So it is super useful to know about gradient boosting and to be able to use it. The next thing is gradient boosting is like very easy to use as opposed to neural networks again. You need to know sklearn interfaces. You need to know how the one function fits. One thing that you need to do, though, is sometimes you need to tune the hyperparameters, but it's pretty easy. And the third thing is that gradient boosting works really well even if you have relatively small amounts of data. So even in that case, you will have a pretty good model that you can use later in production. Because of these 3 reasons, gradient boosting is used in many, many places. It is used in industry. It is used for recommendation systems. I can tell you something about how we use it in Yandex. Yandex is a large Russian company. It's like a Silicon Valley of Russia. We have taxi, search, ads, recommendation systems, self-driving cars, personal assistants, all this stuff. And most of our products are using machine learning, and most of them are using gradient boosting. So our search engine, our search results are based on gradient boosting formula. Our weather prediction is also based on gradient boosting formula. Even self-driving cars or even machine translation do use gradient boosting. Or our personal assistant, this answering for your request, gradient boosting is used in several places there to understand the intent, what the person was meaning, and also to select between the different versions that are generated by a neural network. So gradient boosting is used in many places in production in our company also. Now, how does it work? Gradient boosting is an iterative algorithm. Gradient boosting is usually works with decision trees, and it works as following. First, we build one decision tree so that training error has reduced a little bit. Then we train one more decision tree, so the training error reduces even more. And then we do it for hundreds or thousands or even tens of thousands of times. And then we have a large ensemble of trees, which already can, which helps us have a very low training error. And it's also helps us to have a low validation error. So it is important to understand that gradient boosting is an iterative algorithm to use it, and I'll show you later why. Okay, now a few things about CatBoost. There are different types of data that you can work with. There is numerical data. For example, salary is a number, and when you are using decision trees, then the tree is always splitting your data in two parts. And if you are using decision trees, it's pretty easy to split in two parts because you can split the values, all the values where this value is greater than something, and everything else. It's not so easy if you use categorical features. Categorical features are features with values from some discrete set. For example, occupation is a categorical data, so you cannot compare the values of occupation using greater or less. So you need to do something with categorical data. Occupation is actually pretty easy categorical data. A more complex one would be the one that has a lot of different values, like user ID, for example. And you need to handle it somehow. The good thing about CatBoost is that it handles categorical data out of the box. So as opposed to other libraries, we do numerical and categorical features, and we do categorical features really, really good. Okay. Now, the advantages of CatBoost. The first one is categorical feature support. The next thing, and that is something that our users, that is the first on the list, because that is something that our users usually tell us that is the most important thing about the library. And that is that out of the box, without any hyperparameter tuning, you already get a very good result. That is because we are working hard on having good default parameters. They depend on the data set, and we also have, from the start, we have a large ensemble, so you do not, in most of the cases, you do not underfit. And also we use specific kind of trees that helps us, that helps the resulting quality to have to be less different when you change the parameters. So that is a really important thing, because you do not have to tune the parameters a lot. It saves you a lot of time and a lot of machine time also. So the next thing is categorical features. The next thing is that our library contains a lot of stuff to analyze the model, so to understand why your model is giving you these predictions. Those are three very nice things. There is also a lot of other stuff, but I cannot tell you everything, and it's usually good to remember three things. So if you just remember these three things about CatBoost, it will be good. Okay, now about the quality comparison. Usually when you are trying to figure out which library you want to use, you care about several things. First thing is the quality, and the second thing is the speed. So this slide presents a quality comparison with other publicly available libraries like GBM, XGBoost, and H2O on a set of publicly available datasets in binary classification mode. On these datasets, CatBoost always wins. In some cases, like on Amazon, we win by a lot. On others, differences. So it depends. But Yeah, so there is a whole bunch of data sets where CatBoost wins by a lot. Okay, that is about quality. The next thing is about speed. And in speed, you care about three things. One is training on CPU. Another one is training on GPU, if you have GPUs. And the third one is prediction speed. And that is if you are trying to do some applications, time-critical applications. Like we have search, for example. That is pretty much time-critical application. Okay, now some benchmarks about training on CPU, on GPU, and prediction. The first thing is CPU speed. Currently, the state is the following. On some datasets, CatBoost is the fastest. On some datasets, CatBoost is the slowest. It depends on dataset properties. On large, dense datasets with a lot of data, on large, dense datasets with a lot of features, CatBoost will be the fastest by far. And on small datasets, CatBoost will be the slowest. But we are working on that right now, so I hope soon we will be the fastest in all the cases on CPU. So here is a comparison on two datasets, Higgs and Epsilon. And those are three libraries, and here is the learning time. And those are two datasets. So on Higgs, CatBoost is the fastest one. And on Epsilon, CatBoost is the fastest one. And on Higgs, LightGBM is the fastest one. So yeah, it will depend on the data set if you are talking about CPU speed. With GPU speed, it's completely different. CatBoost is by far the fastest of all the existing libraries. And actually, GPUs for gradient boosting are really useful. With GPU, you get a speed up to 50 times. Or if you are using multi-classification, it can be 100 times. So GPUs are super useful. And at Yandex, almost all our formulas are trained using GPUs. That's why we are focusing on GPUs. OK, here is another useful slide that you should remember. And that is about GPU training. The more data you have, the more speed up you will get from GPUs. If you have a very small data set, there will be no speed up from GPU. But the larger is the data set, the more will be the speed up. So that is the speed up. That is the number of samples. And those are different GPUs. And with CatBoost, even with very old GPUs, you will get pretty good speed ups. If you are interested, you can try GPUs on Google Colaboratory, and we even have a tutorial for that. And Google Colaboratory gives you, I'm not sure, I think it's K80, and you get a speed up with that. OK, that's the CPU versus GPU. I strongly recommend you to try using GPUs for gradient boosting. It will be so much faster. OK, next thing. Next thing is the prediction time. And with prediction time, because we have all these recommendation systems and all this time-critical applications in Yandex, we care about prediction speed. And CatBoost is faster than other libraries 30 to 60 times. And just now we have implemented the GPU applier for our self-driving cars, and it's even faster. So if you care about speed, it's a good choice. OK, one more time. Here is the tutorial data. Please download it. And we will start coding. I'll give you 3 minutes for that, if you have not yet done so. And if already someone has downloaded the data and has questions, you can ask. Yeah?
For GPU training, can you reproduce the results? And sometimes with neural networks, you're not able to. You get a different result when you're running on the GPU. Can you set the seed so that it produces?
Yeah, so on GPU, CPU training is deterministic. Yeah. And GPU training is not deterministic because you use atomics there, and the summation order is all the time different. So the results will slightly different from run to run. Right. That is one of the differences between CPU and GPU. But we use GPUs anyway. By the way, who of you is has GPUs or is able to train on GPUs? OK, nice. Do I need to wait for someone? Please raise your hand up if I have to wait for you. Or everyone has downloaded everything. Okay. Okay, then we will open the tutorial. We will open the tutorial. To do that, you need to run Jupyter Notebook command in the folder where you have this tutorial. And we will start. And tell me if I have to wait for you. Just raise your hands and I will. So I think we can start. We will try gradient boosting using Amazon Employee Access Challenge dataset from Kaggle competition for our experiments. This dataset has the whole set of categorical features. And there is a link to the challenge that you can read about it. Let's start. First, we import CatBoost. And if it doesn't work for some reason, it might be, if it gives you an error, it might be because you have a very old NumPy. If you have not an old NumPy, then it should work. The latest version is 0.15.2, but next week we will have the next version. So keep updating. And I suggest you to check that you have the latest version, at least 0.15.1, because some of the things that I have here in the tutorial there are not present in old versions. Okay, first what we will do, we will read the data. We are reading the data using the Amazon function from CatBoost datasets. Here we have some datasets for our tutorials, and we are adding new datasets there when there is nothing, when we want some specific functionality. And for example, just now we have added there 2 more datasets with monotonic constraints because there were no datasets in open source for monotonic constraints, so we have added Yandex internal datasets. This dataset is not internal, it's external, it's from Amazon, so we will use it. Let's look what is there in this dataset. There are several columns. The first column contains action. And the action is the column that we will be predicting. The dataset, in this task, we want to predict if some person will be granted with some role. And action 1 means that the person will be granted with a role, and 0 means that person is not granted with a role. And we want to predict that. And there is a bunch of features that describe the person and the role and everything that we know about this person. For example, there's the resource, and that is the resource that we ask access to. There is the manager ID, it's the ID of the manager probably that grants the role, and some other features also. What we can see in these features, they are all integers, but they look like hashes, and they really are hashes. So if we try to use them as numerical features, it will work really poorly. We will have very bad quality. Because of that, we are handling them as categorical features, and CatBoost allows you to do that out of the box. So we have read the data set, and we have a data frame with that. What we are going to do now, we are going to build a training data set without labels, so just the features matrix, and we will build a column with labels. And now we will look on the labels. So what we can see here, so what we have done, we first have said that categorical features are all the features that we have. I will increase this. Okay, I think it's better. So categorical features is all the indices that we have in the matrix. So all the features are categorical. And that is the first thing that we have done. And the next thing that we do, we are analyzing our label values in this data set. So what we can see in this data set, that this data set has only 2 labels, 0 and 1, and count of zeros is much less than count of ones. So this data set is pretty unbalanced. And this will have some consequences. But that is just the first thing that we are doing when we are looking on the data set. So we have the matrix, and at least what we can do, we can look on the balance of the classes. And that's it. Now we can already train the model. So training the model is really easy. What we have done, we have built the x and y, x matrix and y vector. X is a matrix of features and y is a vector of labels. And now what we are doing is we are creating an object of type CatBoost classifier, and we fit x and y there. One thing that is different from other classifiers, so that is actually something that you do with all the all the things in Python that you have there. One thing that is different is that we have this cat features parameter, and in this parameter you are passing the categorical feature indices. So the column is indices where you are saying that this feature is categorical. It is also allowed to pass categorical feature names if you want to use strings, but we have indices here. One other parameter that you see here is called verbose, and that controls the output. Because we were training for 100 iterations, and that means that we were training an ensemble of 100 trees. We didn't want to output 100 different lines, which you will get by default, so we decrease the verbosity. Okay? So now we already have our first classifier, and what we want to do, we want to make a prediction. And to do that, you call the function that is called predictproba, and this function returns you an array where for each object you have two numbers. The first number is the probability of class being the object being class 0, and the second number is probability of the class being 1. And that's it. What else you can do to have good results? You can not use this iterations equals 100 and have the default 1000 of iterations, because 100 is never enough. But because we are having a tutorial here and I want everything to run fast, I'm setting the number of iterations to some small value. If you just do this, you will already get a good model for almost every case in binary classification that you have if you have table data. That is the first thing that we have done. Okay, the next thing is creating the pool object. What we have done, we have used x and y here. That is one choice that you can do, and it's pretty useful if you just have the features and the label. But in some cases, you have more things than a feature and a label. For example, you have object weights. And in case if you have an imbalanced data set, that might be very useful. So if you have an imbalanced data set, you might add a new column with weights where you give a large weight for your rare class and a small weight for your very frequent class. Or that is one option. Or you might have something else. So we have for some modes we have like group IDs if you do ranking. So if you have a lot of information, then you can create a pool class. Now, so actually when you are training a model, you do not just want to fit the function without looking on the error. So here we have just fit the function and we just look on the training error. Usually when you are doing machine learning, what you want to do, you want to use a validation data set. So we have this whole trained data set, and now we are going to split it into two parts. One part, like 80%, we will use for training, and another 20% we will use for validation. So what we are doing here, we are creating two objects of class pool. One is called train pool, another is called validation pool. And those are just two parts of the data. Now we will be able to train a model and to look on the validation error and to check if the model is underfitted or overfitted, so we will be able to select a good model. The next thing that we want to do is we want to select the objective function. So for binary classification, there are basically two options, log loss and cross entropy. And the choice here is the following. If you have the probabilities in your labels, then you use cross entropy. If you have 0 and 1 in your labels, then you use log loss. And that is what we have here. So we have selected our loss function. It's basically selected automatically. And if you have multi-class problem, if you have like 5 classes or, yeah, so if you have more than 2 classes, then automatically the loss function multi-class will be selected if you use the CatBoost classifier class. So that is, yeah, but if you have probabilities, then you need to use this cross-entropy error. Okay, now what we have done, we have chosen the loss function. We have split the training data set into 2 parts, train and validation. And we have fitted the model with these 2 data sets, with this line. Now let's look a little bit into what we have in standard output. And to do that, we will train our model one more time. Okay. So we are just training for 15 iterations, and it is important to understand that you should never train for 15 iterations or even 100 iterations. And I am saying that because it really bothers me, because I sometimes see benchmarks comparing the libraries where you have 10 iterations or 50 iterations, and it doesn't make sense. So you better train for enough iterations, and that these 15 iterations are just for tutorial purposes. So what are we seeing here in our STDOUT? The first thing here is saying that learning rate is set to 0.5. And that is something that CatBoost has. So if you do not set the learning rate with your hands, then learning rate is set for binary classification. Learning rate is set automatically for you using the properties of the dataset, like number of samples and number of features and number of iterations that you have. In this case, because we have a very small number of iterations, learning rate is set to a very big number, because otherwise we will underfit. We are underfitting anyway, but yeah. And now what we are seeing here in our log. First, we are seeing the values of training error and of validation error. Those things are decreasing all the time. So learning error will decrease all the time of your training, because training error all the time improves. And the test error or validation error, it decreases while the model improves. And at some point when you have overfitting, it starts increasing. And that means that you should stop here. Now here, the next thing is called best. And that means that is the value of the best validation error and the number of iteration with the best validation error. So if you train for 1,000 iterations or for 5,000 of iterations, then this number will first increase, and then it will stop increasing. It will just have like the iteration 1,115, and you train further, and it doesn't change. Now here, you have the time passed. That is how much time has passed since you have started the training. Yeah, and you can see that you are training for the whole hour or something like that. The useful thing here is the remaining time. So you can always see in the log how much time you will have to wait until this finishes. So that is the estimate of how much time you will have to wait. And it works pretty accurate for gradient boosting and for CatBoost in particular. So you can look on that. Now, we have trained our model, and we have looked on the validation error and on the time. Let's do more. Let's plot something. What we can plot here, what we can plot. To plot something, you need to pass plot equals to true to your fit function, and then you will see the graphs of all the errors that you want to look on. When we are training binary classification, the optimized function is log loss. But it really depends on you what you want to look on. Sometimes you need to you care about AUC in many cases, because it's a really awesome metric. In some cases you care about accuracy. In some cases you want to see F1 metric. So you can look on any of these functions. You just mention them here. We have many functions implemented in the library, and then you can look on the graph here. So there are several graphs. The first one is showing how log loss improves. The dotted line is a train error, and the not dotted line is a validation error. The point here shows the iteration with the best validation error. And it changes, so it plots you the results during the training. You can also look on the AUC here, and you can also look on the accuracy here. So you can see how these metrics change. It's also possible to zoom in. It is nice to zoom in if you want to look at the details in the end. So it is possible to zoom in to have the logarithmic scale and all the stuff. Okay, so that is the plotting during the training. It is also possible to make the plots after the training. So here we will train two models, which will be very different. One will have a very large learning rate. It's super large. You never should use this. And another one will have a very small learning rate. And they both will be trained with 100 iterations, and we want to compare them. So what we plan to see here, we plan to see that this model with a huge learning rate, it will overfit instantly. So you will have this best iteration in the start, and then the error will increase. And the second model with a very small learning rate, it will underfit. So does everyone knows what is overfitting and underfitting? Yeah, so okay, I think I think it's pretty much clear. And now we will compare these two models. So what we see here, we can exclude the learn graphs, and we will just look on the validation graphs. The green line here is the model that with very large learning rate. With very large learning rate, you instantly get this decrease of the training of your training and validation error, but you overfit like after 25 iterations. And after 25 iterations, this all does not give you improvement. It's just getting worse and worse. And the model with a very small learning rate, in 100 iterations, it's very much underfit. So you need much more iterations for conversions. And actually, this line, it will intersect this line, and it will be in the end, it will be much better. Okay, so that is a way to compare different models. Yeah. Okay, the next thing. If you look here, as I told you, there is always this best iteration on the validation data set. On this graph, you can see that after 29 iterations, you overfit. So this whole trees after the 29th iteration, they just decrease, they just increase your validation error. So what we want to do, we really want, if we have overfitted, if this happens, we want to cut our ensemble to the best iteration. So we want to throw away this rest of the trees and not use them. And that is something that CatBoost does by default. And you probably have to know about that because you train the model, and then the resulting model really usually has less trees than you actually say it to have. So if you train without validation, it will have the number of trees that you asked for. But if you have the validation data set, this eval set, then so we trained here for 100 iterations. And we didn't really overfit here. So I think if we trained a bit more, then maybe we will it will reduce more. But here you can see that the best iteration is 96. 97, sorry, and you have 98 trees because iterations start from 0. So we have thrown away two last trees. But so it is, in this case, we did not overfit in the start, but this is important if you overfit somewhere like your last 500 iterations are trash. So what we are doing for you, we are cutting this. But in some cases, you don't want to cut it. And that depends really on you. If you don't want to cut it, there is a flag to disable this behavior. Okay. That is how we are, that is just the explanation of what is the ensemble that you get in the end after you have trained the model. Okay. The next thing. So we already have trained the model. We have visualized the results. We understand what is exactly the model that we get that we get after we train the model. Now let's discuss a little bit of different other stuff. The first thing that we have is called cross-validation, and it's useful to for example, to compare different models. Let's train a cross-validation here. We will train a cross-validation. We will train a cross-validation with 5 folds. And yeah, we will shuffle the data, and we will look what happens here. If you, I told you in the start that our data set is pretty unbalanced. So there is this negative class is very underrepresented. Now cross-validation can be stratified and not stratified. Stratified cross-validation does the following. So the regular cross-validation does the following. It has the data set, it makes the random shuffle, then it partitions the data set into several folds, and then let's say it's 5 folds. And then after that, we are doing 5 different trainings, where we have one of these folds we use for validation, and everything else we use for training. And we do it 5 times. So the stratified cross-validation can be used for classification, and it does the following. When it does the splitting into these 5 folds, it ensures that every class is represented in the same amount in each of the folds. If you do not do stratified cross-validation and you have a very unbalanced data set, then some of the folds will have very little amount or maybe no at all objects of the underrepresented class. By default, CatBoost cross-validation is stratified. So by default, we do this. And what you can see here on the graph is the mean error. So it's averaged among all the folds, among all the trainings. Every of the 5 trainings has its test error on every iteration. So what we are doing when we are plotting this graph, we are averaging the validation errors of all of the 5 trainings, and we plot a mean here, and we also plot the standard deviation. Okay? So this graph shows you the cross-validation for a stratified version. Now what we will do, we will also train a cross-validation that is not stratified. And to do that, we set stratified to false. Okay? We will also see a graph here. And you can see that the standard deviation is much bigger. So you don't really have to look on the numbers. You can understand this from the graph. That's this thing is, the standard deviation is larger. You can see that. And that is because the cross-validation was not stratified. So the different test parts, they had a very different number of this underrepresented class. Yeah, so we also have this point, this one, and it shows you the best iteration for cross-validation, and that is the way how you can. That is one of the ways how you can select best iterations. Best iteration if you don't want to just use a validation dataset, if you want to use cross-validation. Okay, so let's look on what is the result of the cross-validation. The result of the cross-validation shows you the number of iterations, and on each iteration, you have the thing that we have there in the graph. We have the metric mean value for test and for train. And we have the standard deviation. And if you have, if you have mentioned several metrics here, or at least one additional, then yeah, then there will be the AUC will be here and on the graph, and the AUC will be here on the in the table also. One thing though with AUC, as you can see here, and as we saw, I can show you in the previous graph where we had the AUC here. So we had just one line here. It's just the test error for AUC. So there is no training line for AUC. And in cross-validation, you can see the same. There is no column for AUC here. And the reason for that is that AUC is like a super expensive metric to calculate. So you usually care exactly about AUC metric. But that is the one metric that requires a sorting of your whole data set, and it's super expensive to calculate it on every iteration. So we do not calculate it on train. And if you will care about AUC, and if you will want to calculate it, and your training becomes slow for some reason, that might really happen. So you say that my custom metric or my validation metric is AUC, and then your training just slowed down. What you can do, you can set metric period to 10 or to some larger value, and then the metric will be calculated only on every 10th iteration. So it will be much faster. Yes, and that was about AUC, so you do not have the train AUC here. Okay. Now I will show you the next thing. So the next thing is called grid search. We do not have yet our own parameter tuning function in CatBoost, but it will come in the next or in the after next release. So for now, I am showing you the sklearn version of parameter tuning, and I want you to have it here because parameter tuning is sometimes important. So you need to learn how to do this. It's really easy, but I want you to have an example of how to do it here. What does grid search do? Grid search runs training with different parameters, and then it selects one set of parameters where the average validation error was the best. And here is an example. In this example, I will only grid search through a single parameter that is called learning rate. I will not use other parameters because I want it to be fast. So what you are doing, you are writing a grid of parameters here, and then you pass it to the function that is called grid search CV. You train it with the fit function, and then you get the best estimator. What we are going to do here, before you have seen the results, we are training for 20 iterations, so we are training a very small ensemble, and we are grid searching through these 3 learning rates. What do you think will be the best learning rate? Any guess? Sorry? Middle. That is like super small. Actually, this one is also small. And we are just training for 20 iterations. Just 20. So I guess, and I hope it will be right. Yeah, it's right. Yeah, so the best learning rate is 0.5. And the reason is, the smaller is the learning rate, the more iterations you need. And the opposite, the less iteration you have, the bigger you need the learning rate. So if you have a very small number of iterations, like 20, you need to set your learning rate to 1, actually, to be able to train anything. So even with this 0.5 learning rate, the ensembles with 20 trees, they are all underfitted. But yeah, this works together with our intuition. So it shows, it proves our intuition. Okay, that is the way how you tune the hyperparameters. You might tune the whole set of hyperparameters here, and I will tell you about them a bit later. Okay. The next thing. The next thing is called Overfitting Detector. So we will run our training with Overfitting Detector now. As you can see here, we are training for 200 iterations. So we want to train an ensemble with 200 trees. That's our goal. But we are saying that we want to stop training if we see that the training does not improve already for 20 iterations. If you train for several thousands of iterations, then you probably should say here at least 50. Yeah, so 50 is a good value. And if you train several thousands of ensembles. But here we want to overfit with 200 of iterations. So I set it to 20. Yeah, so, and you can see here that we reach some value and then we do not improve. And the training stops. So there are several choices how you can do training. One choice is you do not use Overfitting Detector. You just run for some number of iterations, for example, for the default 1000. And you do not set the learning rate. So you just believe in the algorithm that the algorithm gives you a good learning rate. Then the algorithm selects a learning rate based on the number of iterations that you asked for, and it trains until the end, and it will probably overfit somewhere before the end, so we are trying to make it happen. That is one thing. And another thing is the following. You set the learning rate with your hands to some small value, for example, to 0.03. It's also a very good value. And then that is the default value for everything then, other than binary classification, so it's easy to find. And then you train for many iterations, like you set it to small value, and then you train it for 10,000 of iterations, and you use the overfitting detector. And it will stop at some point when you see overfitting. So it depends on you. One thing that you will not get here in when you are using overfitting detector and you are training for like 50,000 of iterations and you stop using overfitting detector after first 2,000. One thing that you do not get right in this case is the time estimate of how much longer we will train. I have shown you in the standard output this last column that shows remaining time. And it's pretty accurate, but only if we do not use overfitting detector, because we really cannot know in advance when the overfitting will happen. By the way, you can see the same numbers here. So there is a time estimate. One of these things is time estimate of how much time is left, and another is so the one with this thing is the time estimate, how much time is left, and it changes during the training. And another one is how much time has passed. Yes, so it depends on you what you want. But basically, if you don't care about this time estimate, you can just use overfitting detector, set 10,000 of iterations and small learning rate, and it will stop for you. Okay, that was the overfitting detector thing. Yes, so what do you think how many trees you will have there? So we have here the number of iterations is equal to 200. But we didn't train 200. We have stopped here, and that is the best iteration, the 41. And we trained 61 trees, 62 I think, because the iterations are zero-based. So what do you think? What will be the model with early stop dot tree count? Any guess? Yeah, exactly. Yeah, it will be 42 because it's zero-based. Yeah, that's right. Yeah, so even if you do early stopping, you still will throw away all the iterations that are after your best iteration. Okay, nice. Yeah. The next thing. So the next thing that I want to tell you is called eval metric. I already have shown you this custom metric parameter, where we are plotting the whole set of different metrics. And that is just the way, the way to look on the metric values. It doesn't do overfitting detector, or it doesn't cut the trees using this metric. So you select the best iteration using some metric. And for binary classification, it is log loss. And all the metrics, all the other metrics that you have put into your custom metric field that we are plotting, all those metrics are not used for early stopping. So early stopping is done using log loss. But sometimes, if you really want to optimize other metric, if you really want to optimize AUC, and you want to do early stopping using AUC, you want to do this cutting of your ensemble using AUC, then you should use the eval metric parameter. So let's train it with eval metric. Now the eval metric is the first one here. And it will be used for both. It will be used for overfitting detector, and it will be used for early stopping. So what we will have here, so the log loss is also overfitted. But the log loss is overfitted on the iteration 41, and AUC on the iteration 42. So the tree count should be the tree count should be 43. Oh, maybe I have done something wrong. Okay, so the eval metric is used for, it's used for early stopping and for selection of the best iteration. Okay. Okay, let's go to model predictions. We now have trained we now know everything about training. We know what graphs we can plot. We know how we cut the trees and all this stuff. And now let's do predictions. So for classification, for binary classification, there are a few ways of doing predictions. So we will first train another model for 200 of iterations, and then we will do predictions in all the ways that we can do. There are 3 ways of doing predictions in binary classification using the sklearn interfaces and using our interfaces. The first one, and that is the one that you should not use, is called predict. So the predict method gives you the class value for your object. So the value of the predict function is either 0 or 1, and that is done in the following way. You predict the probability, but you want to decide which class you will use, and if the probability is greater than 0.5, then it is you have the 1 here, and if it is smaller than 0.5, then you have the 0 here. Okay, the 0.5 border is actually not, usually it's not the best solution for you. So sometimes it's better to select your own border. I'll explain this in a minute. So what you can use predict proba. Predict proba is the second way of making predictions, and it gives you the probabilities. For each object, there are 2 values. The first one is probability of being 0. The second one is probability of being 1. And they sum to 1. Okay? So what gradient boosting does, it builds the trees, and then when it is doing predictions, it applies them in the following way. You have the first tree, you go through all the splits, so this feature greater than 1, this feature is greater than 2, and so on. You get to the leaf. In the leaf, there is a value, a numeric value. You get this value. You go to the next tree. You do the same, you have the next value. Then you sum these 2 values, and then and so on. And then prediction is the sum of all those values. And that's for any mode, not only for binary classification. But for binary classification, we want to have a value between 0 and 1. The sum of all the trees cannot be a value between 0 and 1. So in binary classification, we are using the sigmoid to make the probability out of the sum of the trees. So really, the sum of the trees is not a probability. It is not a value between 0 and 1. It's just some real value. And then you calculate sigmoid on top of that. So let's do this. So there is the prediction type that you can pass to the predict function. And this prediction type is called row formula value. And as you can see, and that is just the sum of the trees. For regression tasks, it will be your answer. But for binary classification, it's not your answer. You get the sigmoid on top of that. And that looks like that. Now, why I am telling you this? This is important. This will be important when we will be trying to analyze the model. So when we will be trying to understand why the model is having this particular value and not the other value. Let's write our own sigmoid function. It's pretty easy. That is the sigmoid function. And let's now check that our probabilities are sigmoids of the row formula values. Okay? So we have here row formula values. It's in the row pred field. We have calculated them here. Now we will calculate a sigmoid on those values. And we will get some values. So let's see that these values are equal to these values. Okay? So let's look on the first object. The first object, it's a probability of the sigmoid of the row formula value is the probability of having class 1. So it should be in the right column in the predict proba function. Okay? So it's exactly what you see here. So for the first object, it's 0.9714. Okay? So that is how we are doing the binary classification. Are there any questions now? Okay, no questions, good. Or not good, I don't know. The next thing about binary classification that you have to know is how you decide if you want to call this object positive or negative. As I showed you, this basic predict function here, it is just using the 0.5 border. But in some cases, you don't really, so in some cases, the 0.5 border is not the best choice. So now I'll try to explain you how you can choose better. So how you can choose better. If you have your own task, then what you care about is you either care about, when you are saying that the object is positive or negative, you either care about false positive rate or you care about false negative rate. So in some tasks, you don't want to have any false negatives. For example, let's say I'm a doctor and I'm using the classifier to make the pre-analysis of the person, and I'm saying if the person is sick or not. If I'm saying the person is maybe sick, then he will go to a second exam. So what I do not want to do, I do not want to say that the person is not sick. So I do not want to say that the person is definitely healthy if there is any chance that the person is sick. I want him to go, or her, to go to a second examination. And here I care about false negative. I don't want to have false negative. I don't want to say that the person is not sick. And, or there might be a case where I care for false positives. So what you want to do, you want to make a decision what you care about, what is a false positive rate or false negative rate that is good for you. Then you can plot a curve or with false positive rate or false negative rate. Here on this graph, I plot both of them. On this graph, here is the probability threshold. Okay, it's from 0 to 1, and to every threshold, there is a point of false positive rate or false negative rate. So let's say that I care about false positive rate, the blue one. So I select the error rate that I want on this graph, And then I see what is the threshold that I want to get. Okay? So you can look on the graph and select that, but you can also, there is the select threshold method, there is the select threshold method where you just pass the false positive rate or false negative rate that you are okay to allow. So in this case, for our data set, I am selecting a threshold for 2 different cases. In the first case, I select a threshold where I'm saying I allow no more than 1% of false negatives. And in the second case, I am saying that I'm allowing no more than 1% of false negatives or of false positives. And as you can see, the threshold that I get for those requirements, the thresholds that I get for those requirements are really different. So the second one is almost 1, because for this problem, it's really hard to get such a false positive rate, okay? So that is the way how you, if you are doing binary classification and making a decision, if you are not ranking the objects, so if you not only want to see which of the objects is more positive, if you want really to make a decision that this object is positive or negative, then you should select the threshold more smart. Okay, so now we are able to do predictions for binary classification. We are able to train the model. We are able to do predictions for binary classification. Let's now analyze a model a little bit. So the first thing that we will be doing, we will calculate metrics on a new data set. Sometimes you have a model that is already trained. And you have your new data set, like for example, I have the old data and I train a model on old data, and then I want to check if my new data that has just arrived, how well does this model handle this new data. To do this, we have this eval metric function, and you can look on different errors here. And as I told you, so one thing is called eval period, and that is on which iteration you evaluate a metric. So if you calculate metric values, and it takes a long time, which you will get with AUC metric, then you can increase this eval period to some larger value than 1. And then you can look how your metric value changes, not on every iteration, but on every 10th iteration. But anyway, yeah, you have those graphs here. You have also, so the function returns values, of course. So it returns, in this case, because we were calculating AUC metric. So we call the metrics, metrics is the result of that function. We call metrics AUC. And then we can look on the values of this metric on every iteration. So that is the way to see if your model does still good on the new data, okay? It's also possible to pass your own metric here. So you can write a Python metric, or you can write a C++ metric and use it here for metric calculation. Let's go to feature importances. So that we want to understand which features of my whole data set, which features are the most important ones, which features are the least important ones, and maybe I have some features that I would better remove. So maybe some features are not good at all. There is the whole set of analyzing feature importances. The first one is called prediction value change. And that feature importance shows you how much, on average, prediction value changes if there is a change in this feature. This feature importance has few very nice properties. First one, it's super easy to calculate, so you get these values instantly. And the next one is all those values are positive, so they can be normalized, and we do normalize them. So they are all they all sum to 100. So you can see a round histogram, what is the name of this, and see what is the part of the importance of this feature into the whole. So they all sum to 100. These feature importances work really well, and we use them a lot in Yandex. But in some cases, like for ranking modes, those feature importances are might be misleading. So they might be misleading only for ranking. So for everything else, like for binary classification, they work really well. But yeah, there is the next type of importance that I want you to know, and that is called loss function change. So the first one was telling how much prediction changes if you change the feature. And the next one tells you how much on average your loss function changes if you are changing a feature value. What we are doing here, we are trying to simulate the following process. We are training the model with the feature. And then we are training the model without the feature. We do not do this, we approximate this process. And we are saying, we are looking on how much the loss function value changes if I just remove this feature and retrain. In reality, what we are doing is we are just removing this feature from all of the trees. And then we are averaging leaf values, and we are saying that this would be the ensemble that I would get if I would remove this feature. This loss function change, this type of feature importance, it works really well, and for all the modes, including ranking modes. But it has the disadvantage that it is time-consuming to calculate. So for some datasets, especially for very large datasets, it might take some time to calculate, but it's not super slow, so you can do that. These feature importance values, they might be positive, and they also might be negative. And they are negative if the feature is not good. So if you would better remove this feature, then the feature is negative. Here, all the features importances are positive, so all of the features are fine. But one thing about this loss function change importances is you might get a negative feature importance for some feature. And you will think that it means that this feature is harmful. Sometimes, if your model is underfitted, if you train the model for 20 iterations, then some feature is giving you a negative importance just because without this feature, it would be easier to train 20 iterations. So if you train for more iterations and if you wait for overfitting, then this feature will get a positive importance. So there are two things that you can think about when you see a negative importance. The first one is that maybe the feature is harmful. And the next one is maybe I'm doing something wrong, maybe my ensemble is underfitted. And then I overfit my ensemble, and then if it's still negative, then it's harmful, I remove it from the model, okay? Those are two ways of measuring feature importance for the whole data set, or for the whole model. So how important is this feature for a model? But there might be a different thing that you would be asking. And that is, if I'm doing prediction, and on this particular object, I have some value of the formula. And now I want to understand for this particular object. Why for this particular object, because of which features, do I have this value? And for that, we have a different thing that is called Shap Values. Shap values are calculated per object. So each object has a set of Shap values, and those are one baseline value that is the same for all the objects. And then there are importances of all the features. All these importances, they sum to the prediction of the object. And that is a very nice thing about Shap values. So your feature importances sum to prediction. One thing about binary classification that I told you is that the real prediction, so the real sum of the trees is not the probability. So it's not a value from 0 to 1. It's some value from minus infinity to plus infinity. So this for binary classification, Shap values are summing to this value, to the initial value, not to the sigmoid. Okay? So let's look on some objects. I have selected here two objects. One has a very positive prediction. It's almost 1. And another has like a less positive. It's more like a negative, more like a negative object. So let's look on how those things are explained here. First, we are looking on the first object, which is super positive, and we are looking how it is explained. There is the baseline value, and you can see it here. It's called base value. And that is the point where we are starting. And that is the point that is the same for all the objects. Then we are starting from this base value, and we are adding the importances. Because of some positive feature, I go to the right. Because of some other positive feature, I go to the right. And so on, and I make some steps to the right. Then because of some negative feature, I go to the left, and so on, and I end up in the prediction of this object. So for this particular object, the feature with the most positive influence is called manager ID. The next one with a very large positive influence is called roll-up 2, and so on. So you can look on this plot and understand what are the importances of different features. It is a little bit tricky with categorical features. So with numerical features, those importances, you can not only look on the importances, you can also look on the value of the feature. And you can see that the greater is the feature value, the more positive is the importance, or the opposite. And with categorical features, you cannot really do that. It will be just you have a big positive influence of manager ID. That means that this manager ID, for some reason, has a positive influence. And that actually means that the numerical features that are calculated inside the algorithm based on this manager ID feature, they give this positive influence. But it doesn't say anything about the absolute value of manager ID. Okay? So the next object that we are looking on is more negative. So there is this base value that is the same for all the objects. And because we had this very unbalanced data set, this base value is very much to the right from 0, okay? And yeah, so because of roll code, the roll code has the largest negative influence. And yeah, you can look on the importances of all the features here. The visualization is done by the Shap library. Does it work? Does the Shap library work for you? Is there anyone having problems with visualization? Okay. Are you having problems with visualization? Did you install a library?
Yeah, I was just checking with that.
Yes, so Shap library, it's a super nice library, but at some point, I think they stopped supporting Python 2.7. So yeah, but the visualization should work in Python 2.7. And there are several ways of calculating Shap values. You can calculate them using CatBoost code, or you can calculate them using Shap code, because CatBoost is also supported in Shap. And the Shap part, it will not support Python 2.7 starting from some version. So it's more safe to use CatBoost code and visualization from Shap. Here is the import Shap thing. And if you have not heard about this library before, I recommend you to look into this. They have a GitHub repository, and they have a bunch of tutorials on different gradient boosting libraries, on neural network libraries, and they have really nice visualization of model explanation. So I recommend you to look into this one. Okay, the next plot that we will see here. The next plot is just showing the importances of all your data set, of all the features on all your data set. They are ordered by the importance to the model. The most important feature to the model appears to be manager ID. What we can see on the graph here, you cannot, or you should not look on the colors in case if you have categorical features, and that is what we have here. So don't look on the colors, just look on the shape. And the shape here shows the following. This axis is the importance value. So it's the impact of the feature. It is negative if it's on the left from 0, and it is positive if it's on the right from 0. Now let's look on the manager ID. One dot shows you one object, okay? So as you can see that for many dots, manager ID has a very large negative importance. And for many, many other objects, manager ID has small positive influence. And that is something that you can see for every feature. It's super interesting in some cases to look on this particular graph, especially if you have numerical features. With categorical features, the color doesn't show anything. That's a problem. But yeah, you still get useful information. Okay, that was the model. That were the things about model explanation. We actually do have in the library much more stuff. We have object importance, so you can understand what are the samples in the training data set, which were the most important for the loss function. We have the model selection thing that is called eval feature. So there is a way to evaluate if the feature, if you should add this feature to your model, and you will get a statistically significant improvement. So we have a bunch of stuff there, and we will be adding more. So in the next few releases, we will add more stuff. Stay tuned. Okay, the next thing I want to show you is snapshotting, and I really want you to remember that. Sometimes when you are training the model, and you have a large data set, and you are training for thousands of iterations, it might take a while. So it will take for a few hours, or maybe it will take the whole day. And if you are training on your laptop or even on the server, the laptop might go to sleep, or the server might go down, or something might happen. So it is a good idea, if you have a long training, to use snapshotting. It's super easy. You just use the parameter that is called snapshot file. Okay, I will remove this first. Yeah, we have started training. We are training, and I stopped. Now I stopped. There was a keyboard interrupt. And now I will train one more time. And you will see that we trained for 100 iterations, and we stopped after the 80th iteration. Now we are proceeding from the point where we have stopped, okay? So if you have a long time training the model, use snapshots. It's really almost free. It's saved like by default every 15 minutes. I think so. Maybe yeah. So it's by default it's saved every 15 minutes. But you can set snapshot interval to something, and I have set it to 1 second because I wanted to show you that it works. But yeah, by default it's just saving every 15 minutes. Okay. Now the next thing is saving the model. You can just save the model as a binary, and then you can load it back. It's super easy, and yeah, so you are saving the model to the file, and then you can use it in production. Our binary format is a very good format in terms of how you will application speed. So if you will use JSON, or you convert it to C++ code or something else, it will be a bit slower. But you can still save it in any format. So there is a bunch of things you can save it in. There is an Onyx format, Cormel, I don't remember. So there is the bunch of formats, and I think everything that you want is covered there. Okay, and there is a couple of words that I want to spend on hyperparameters. So I will run it. And I will run it for 1,000 iterations, and I will just tell you about a few parameters that you need to know about. So the one most important parameter that you care about is learning rate, in pair with iterations. So what you want to do, you want your model to overfit a little bit. So you do not want it to overfit a lot, but you do not want it to be underfitted. So you want to look on this graph always and see that this best error is somewhere close to the end, okay? If it is not close to the end, so if it is in the end, if it is the last point, then what you are doing, you increase the number of iterations. Or you increase the learning rate. Better you increase the number of iterations. Okay. And the next thing, or if it's overfitted is somewhere in the middle, then you do the opposite, okay? So one thing you can do is you can run with default number of iterations, and you can and you are not setting the learning rate. Then the algorithm sets the learning rate for you, and it's somewhere close to the good one, but it's not the best one. So if you are looking on the graph, you can use this graph and use the value that you see in standard output or in model parameters, this learning rate, and then you attach it a little bit. So you either increase it a little bit or decrease it, okay? The next thing is called depth, and that is the depth of the tree. One thing you should do, you should try depth 10. So you try the default one, 6 works well in most cases, but in some cases you need deeper trees. Well, there are some cases where you need deeper trees. Then you try 10, and if 10 works, then you can adjust. You can try 8 or 12. And if 10 doesn't work, then it probably doesn't make sense to try those increased values of depth. It is also not a good idea to set the depth to 16, because what we do in CatBoost by default we are building full symmetric binary trees. So it is a full binary tree. So if you have the depth 16, then the number of leaves in every tree will be 2 to the power of 16, which is a lot. So it's not what you want to do. It's not the same. So for example, in light GBM, the strategy of building tree is different. So depth 16 doesn't mean there will be a large number of leaves, because it's growing not a full binary tree. It's growing not symmetric tree. Actually, in CatBoost, you also can. There are several tree growing strategies that you can use. There is the default one, this full binary symmetric trees, but you can also use depth-wise, not symmetric tree, like XGBoost, and you can also use the loss guide, like in light GBM. So those 3 strategies you can use. The second and the third are implemented only on GPU, but we are currently working on adding them on CPU also. How you should select among them? Actually, the loss guide strategy works well if you have one hot encoding, or if your data is not noisy. So it comes from like the Higgs dataset. So it comes from the physical simulation, for example. So for datasets that come from some simulation and have no noise or a little amount of noise, and for one hot encoding or a super sparse dataset, it's good to try the loss guide strategy. And for noisy datasets, it's good to have the symmetric ones. Okay. And here I have 3 more parameters, and you can just play with them. You can just tune them. They are staying here in the tutorial, so yeah, you can play with them. Also, if you open the docs, we have a very detailed documentation on many things, including how to tune the parameters. The next block here is just listing the set of parameters that you can play with to do the speed up. And here is the list of the parameters that you can play with. If your model is large, for some reasons, if you have categorical features with a lot of different values, then the model might be large. So if you have this problem, then you play with those parameters. Okay, and we have our site. It's called catboost.ai. Okay, I will go to the slides. Yeah. Sorry. Yes, so we have our site. It's called CatBoost.ai, and there is a very detailed documentation. So I recommend you to read it. It tells you everything about parameter tuning, speeding up the training, reducing model size, and a lot of other stuff also. We have our Twitter account, and we have ways to communicate with people who are using the library. We actively are chatting with all our users, and we have a set of ways to do that. The Twitter account is basically for posting news, but those two things, the Telegram and the Slack, are for chatting. The Telegram account, there is one in Russian, it's called CatBoost RU, and there is the one in English. So if you have any questions, you can ask it in the chat, and there are different people who are using the libraries who can discuss it with you, and there are us, we always are reading that and answering. And the next thing is the Slack channel. There is this Slack community, it's mostly Russian speaking, but it's like the largest data science community in Slack, and I'm sure if anywhere there is a larger community, it's about 30K people. The community is called ODS, and there is a bunch of channels in there, and we also have a channel, our channel in there. The channel is called Tool CatBoost, and people are asking questions. There are a lot of Russian questions, but if you ask something in English, you will definitely get an answer from us and from other people also. Yeah, the slides, there is a link with the slides, and now I will also tell you a few words about what we are working on. We are currently adding text features and embeddings as input data types, which will be super nice. Because it will work out of the box with text together with numerical features. We are adding sparse data support. It will come in the release after the next one. And we are adding new methods for model analysis, more metrics, and training speedups. And I have like 5 minutes for questions. Okay. Yeah.
How does CatBoost deal with the high cardinality categorical variable?
Yeah. So what we are doing with categorical features is we are calculating different numerical features on top of them. If you have a high cardinality categorical feature or any other categorical feature, we are calculating statistics that are similar to target encoding, but they are based on some random permutation. So if you have binary classification, then a new feature value that is based on categorical value will be the average label value given this category value. But this, if you do it like that, then it doesn't work. So what we are doing a random permutation on the data, and then we are using only the objects before this one in the permutation to calculate those averages. And we are using also several priors in this formula, and we are calculating statistics based on categorical feature combinations. And we use one-hot encoding for features with a small number of values.
Is there a threshold that you can sort of customize?
Yeah, so there is a parameter that is called one-hot max size, and you just set this one. For lower, you have one-hot encoding. For greater, you will have statistics. If you have anything that you want from the library, you are also you can ask me to add this, and we will probably add this at some point.